Hi. In this set of lectures, we're going to talk about Markov models. Now, Markov models are really simple. They consist of just two parts. First thing is there's a set of states. So those are states that a person's psyche could be in. They could be the state of a particular government or an economy. And then there's going to be transition probabilities. And the transition probabilities are going to tell us the probability of moving from one state to another. So remember all the stuff we learned about probabilities, how they sum to 1 and that sort of thing. All those rules are going to apply here, but the probabilities are going to tell us how likely it is to move from, say, one state to another. Let me give a couple examples. So first, let's suppose we have some students, and those students could be in either one of two states. They could be alert or they could be bored. Now there's going to be some probability P that they move from alert to bored, and maybe some probability Q that they move from bored to alert. And over time, students are going to be moving back and forth from the alert state to the bored state. And the Markov process will give us a framework with which to understand how those dynamics take place. Now, alert and bored students don't seem maybe that important, so let's do something more relevant. Let's talk about countries being free or not free. So those are the two states. A country can be free, a country can be not free. Then what we can do is we can look at data and ask, well, what's the probability that a state moves from free to not free? And what's the probability that a state moves from not free to free? That'll also be a Markov process. So if we look at historically the number of free states and not free states, and then create a third category called partly free, which is the red line, we can see that there's these different trends, right? The free states seem to be increasing, the not free tend to be decreasing. What we can do is we can use Markov process to figure out where is this process going to end up. Are we end up with all free states? Or are we going to end up with maybe some moderate number of free states and the process still churning? That's where the model is going to help us. Now remember we talked about the different sorts of things that processes can do. They can go to equilibria, they can be cycles, they can be completely random, or they can be complex. What we're going to find is as long as just a few assumptions hold, that Markov processes are going to be here. They're going to go to equilibria. And so there's a theorem called the Markov convergence theorem. And this Markov convergence theorem tells us as long as a couple of really mild assumptions hold, namely they got like a finite number of states and those probabilities stay fixed. And then one other thing, you can get from any position, any state to any other state. Then what we'll get is the system goes to an equilibrium. So this is a really powerful thing and has all sorts of implications that we're going to flesh out as we look more deeply into the model. Now to do this, to understand Markov processes, we're going to have to introduce a little bit more notation and another technique, another tool for understanding models. And these are called matrices. So matrices is really just like a little grid, like a 2x2 or 3x3, where you put numbers in here, like 0.4, 0.5, 0.6, 0.5, and those will be the transition probabilities. So what we're going to learn how to do is we're going to learn how to multiply by matrices in order to understand these Markov processes, and in particular to understand how the Markov convergence theorem works. We'll use these matrices to explain why these systems go to equilibria. Now the reason we do Markov processes is twofold. One is they're really sort of a useful way to think about how the world works, and we get this really powerful result, the Markov convergence theorem, that says these systems are going to go to these equilibria. Any Markov process goes to an equilibrium. Second reason we're going to do them is what we talked about in the previous lectures, this idea of acceptation. That the Markov model is incredibly fertile. Once we have the Markov idea in our head, once we understand what a Markov process is, we can apply it in a whole bunch of different settings. In fact, one of my colleagues, when you give him almost anything, he'll say, oh, that's a Markov process. And there's a sense in which a lot of things are Markov processes, and it's often really, really useful to think of things in the context of Markov processes. It's also true, once we have this idea of transition probabilities and matrices, we'll see that we can use those in a lot of settings as well. Okay, so let's get started. We're going to start out by just doing very, very simple Markov process. Then what we're going to do is we're going to look at a slightly more complicated one and then see how the Markov convergence theorem works. Once we've got all that in play, then we'll go back and talk about acceptation, where we can apply it in other settings. Okay, thanks.